Okay, so as usual, we're going to go over the solutions of the checkpoints of last time. There were two checkpoints. The first one is this one, and that was the question. The correct answer is false. You cannot have a delay guarantee. Essentially, the transport protocol service, you have TCP and UDP, and none of them can give you a delay guarantee. The simple reason being that the queuing delay is something that depends on the congestion. Okay, delay guarantee. Delay guarantee simply means that the transport protocol will guarantee that a packet will take less than, let's say, X millisecond to go from the source to the destination. Okay, so because on the internet we have the queuing delay, which fluctuates and depends on the congestion level, there cannot be any delay guarantee, no matter whether you use TCP or UDP. Correct. There's no protocol service. Well, the short answer is yes. However, as we will learn later in this class, on top of the basic network services, the IP, the packet switching network, it is possible to implement additional mechanism which can give some amount of delay guarantee. But when we just talk about just the packet switching network as is, you cannot have a delay guarantee. Okay, so later in this class, we will learn more about mechanism like MPLS, which can provide some amount of guarantee. Okay, and then we have another checkpoint, which is this one. And here, to answer correctly this question, you need to keep in mind what we learned about what happens at the TCP server. At the TCP server, there is always a special socket, which is called the welcoming socket. And that welcoming socket is always open. Okay, and now when there is a client who wants to set up a TCP connection with the server will create a new socket, and that new socket will be dedicated to communication with that client. So if we have 500 clients, we are going to have 500 new sockets at the server, plus the welcoming socket. Okay, so the number of TCP open sockets at the server is 501. So the correct answer is none of this. Any question on the checkpoint? Let me check if I address all the chats. Okay, so there's okay, open socket is a socket that has been opened and that is not closed. Essentially, when you create a socket, you open the socket. So that is a term that I use in the lectures, so opening a socket and closing the socket, right? So when the TCP connection is closed, then the socket that is closed at the server side will be the new socket, but not the welcoming socket. Okay, so let's continue where we stopped last time. Right, so the idea here is that, okay, we want to dynamically adjust the timer value right? And the main input as to how to adjust the timer value will be, actually, sorry, I think I have let me change the settings here. So obviously the timer value should be at least equal to the round trip time. So the first thing you need to do is to measure the round trip time. Okay, the sender will measure the round trip time, and that measure will be referred to as sample RTT. So it's just the raw measurement of the round trip time. Now, the thing with the sample RTT is that it fluctuates a lot. So if we look at this plot, which I think is an actual plot, actual round trip time measurements, what we have in blue are the sample RTT values. So you can see it can be as low as 200 milliseconds. It can go all the way up to almost 350 milliseconds. Okay, lots of fluctuation. So the first thing we need to do is to smooth out the fluctuations. And we're going to use this formula to do the smoothing out. Okay, so this is a recursive formula so that the sender will continuously measure the sample RTT. And whenever there's a new value of the sample RTT, then the estimated RTT will be updated using this formula. So here we have the old estimated RTT value. Here we have the new estimated RTT value, and we have the sample RTT value that has just been measured. So alpha is the parameter in the formula, and the typical value for alpha is 0.125. Okay, the reason this is typically used is that 0.125 is equal to 1 over 2 to the power of 8. 2 to the power of 8, right? If you divide by 2 to the power of 8, you multiply by 0.125. Okay, so why use the 1 divided by 2 to the power of 8? Essentially, if you choose this value, then you can very easily calculate. So instead of having to multiply a value by 0.125, you can just do a shifting. You shift to the left, right? So when you have the binary representation of a number, whenever you shift to the left, you divide by 2. So to just do a shifting to the left 3 times, and that is equivalent to multiplying it by 0.125. So keep in mind that this TCP has been around for quite a while, and when they designed TCP, it was still in those days where the computing power was not so great, right? So they came up with this idea so that you can, instead of having to multiply by 0.125, you just shift to the left, to the right, shift to the right 3 times. And that can be done very, very fast. Okay, so if we apply this formula to the sample RTT shown in blue, we get the curve in purple, which is the estimated RTT. So here you can see that it is much more smooth, right? Because we take the average. Okay, so now we have the estimated RTT, but we're not quite done yet because we are going to add a safety margin to estimated RTT. And the idea here is that the value of the safety margin will depend on the recent history of the estimated RTT. So if the estimated RTT has had a lot of variations in the past, we are going to choose a larger safety margin. The idea here is simply that if we have seen a lot of fluctuation in the recent past, there's a good chance that we will experience also large fluctuations in the future, in the near future, right? So if there's going to be large fluctuation margins, so fluctuation in the values, then we'd better assign a larger value for the safety margin. So in order to calculate the value of the safety margin, we are going to use this formula. And this is deviation RTT. So this is also a recursive formula, right? So whenever you have a new sample RTT, you can calculate estimated RTT, and then you can calculate this quantity. And you use this formula. And in this formula, dev RTT is the old value. And you apply the formula to come up with the new value of dev RTT. And here we have another parameter, which is beta. And beta is typically 0.25. So here 0.25 is 1 divided by 2 to the power of 4. And that is for the same reason as before, because then you can, instead of having to multiply, you can just shift to the right 4 times. Oh, sorry, 2 times. 2 times, sorry. 1 divided by 8 to the power of 2, right? Sorry, 1 divided by 2 to the power of 2. So you shift to the right 2 times. And then finally, once we have the dev RTT, we're going to use it as the safety margin, but multiplied by 4. Okay, so 4 times dev RTT will be the safety margin, and we add that to the estimated RTT, and that will give us the timeout interval, which is the value that is used for the timer. So this timeout interval is continuously calculated, continuously updated, based on the sample RTT that are measured. Any question here? Okay, so TCP does reliable data transfer. And these are the things we have seen already, but just to refresh our memory, it is a pipeline protocol, meaning it uses a sliding window. It does cumulative acts. It has a single timer for retransmission. Okay, so now retransmission will be triggered whenever the sender thinks that the packet has been lost, right? So how does the sender detect there is a packet loss? There are 2 ways it can detect. First is timeout. So this is not new, right? We know if we wait for the app and the app doesn't come with timeout, so we consider that the packet has been lost. But in TCP, they also have another way to detect packet loss, which is duplicate acts. So we'll see shortly in a few slides why and how we can use duplicate acts to detect packet losses. Are they used together? Yes, meaning that whenever there is a timeout or a duplicate acts, it is considered packet loss, right? So it's not going to use exclusively timeout or exclusively duplicate acts. So any of these 2 events will be considered packet loss. All right, so let's first look at the kind of a simplified TCP sender. We're going to ignore the duplicate act. So just assume that packet loss is detected by timeout only. And we also ignore flow control and congestion control. For the flow control and congestion control, we will have another unit dedicated to that. Okay, so let's see what happens at the TCP sender. When the TCP sender receives data from the application layer, then it will need to create a segment, right? Build a packet, if you wish, with a sequence number. And remember, the sequence number is the byte stream number of the first byte in the payload, in the data payload. Okay. And if there's not already a timer that is running, it will need to start a timer. And that timer is a timer that is associated with the oldest unacknowledged packet. The timer value is set to timeout interval, which is that value that has been calculated, as we have seen in the previous slides, right? Where the value is continuously updated, right? So whatever timeout interval has been calculated last will be used for this timer. Okay, the first type of event at the sender is a timeout. If there is a timeout, the sender will retransmit the segment that caused the timeout. Okay, so remember, there's a timer associated with the oldest unacknowledged segment. So when the timer times out, it will retransmit that segment. And then it will restart the timer because we cannot be sure that the retransmission will go through, right? The retransmission may be lost. In that case, we also need to have a timer so that when it times out, we retransmit again. Okay, another event is an ACK is received. So if the ACK unacknowledged previously unacked segment, remember the ACK is a cumulative ACK, right? In TCP, it's a cumulative ACK. So if the sender receives, let's say, ACK of 10, that means that everything, all the bytes, have been received up to byte number 9. Okay, up to byte number 9. So the sender can mark as acknowledged all the segments that are up to byte number 9. And then if there are still segments which are unacknowledged, so note that here when the sender receives an ACK, then so previously we had some timer running, right? Which is associated with the oldest unacknowledged segment. If the sender receives an ACK, then that unacknowledged segment is no longer unacknowledged. And if there are still some unacknowledged segments, so for example, if the sender receives ACK of 10, but if it has sent bytes up to byte, let's say 100, right? So that means that all the bytes from 10 to 100 are still unacknowledged. So the sender needs to start a new timer to wait for the ACK of those which are unacknowledged. Okay, so let's look at the FSM for the TCP sender. So as usual, we have initialization. These are the initialization step. And here we use the same terminology as before for the sliding window. So we have the next sequence number. We have the send base. So here in TCP, the numbering of the bytes does not necessarily start at 1 or 0. Okay, so the very first byte, the very first data byte that is sent on the TCP connection has some sequence number that is called the initial sequence number. And the initial sequence number is chosen by the sender. So it could be any number. And that is called the initial sequence number. Okay, so initial sequence number is assigned to next sequence number, meaning that if the very first segment that will be sent by the sender will have that initial sequence number. Also, the window will start at that initial sequence number. Okay, so the sender is waiting for events to respond to the events. The first type of event is data received from application above. So there is some data that the sender needs to send using TCP. It's going to create a segment. It uses a sequence number for that segment, the next sequence number. Now, next it has to use the services of the network layer below to send the segment. So it will pass that segment to the network layer. IP is the network layer. And then it needs to update the next sequence number. So here, it's going to add the length of the data that is sent in this segment. Okay, remember what I showed you last time? We had, I think the sequence number was 51 for the first segment. And then for the next segment, it was 156, if I remember correctly. And that is because the length of the data was 105 bytes, right? So we just add that the length, how many bytes we send in this segment, and that will give us the next sequence number. Okay, check if there's a timer running or not. So if there's no timer, that means that the segment that we're going to send is going to be the oldest unacknowledged segment. So we need to start the timer for that segment. Okay, the other type of event is the sender receives an ACK, and that ACK carries a number, right? Every ACK carries a number, and the ACK carries a number Y. Y is the ACK number. So it's going to check if the Y is greater than send base, meaning that the ACK that it's received is actually ACKing some segments in the window, right? Greater than send base, meaning that it is in the window. Send base is the lowest sequence number in the sender window. If so, if the Y is falls within the window, here it's going to slide the window. Okay, update send base simply means sliding the window, and the window is now slided to start at Y. Remember, if the receiver receives up to byte number 9, it will send ACK of 10, right? ACK of 10. So to take that example here, the sender will update the window so that now the window starts at sequence number 10. And then if there are currently unacknowledged segment, meaning there are still some bytes in the window which are not yet acknowledged, it needs to start a timer, because we need to have a timer for the segment that correspond to byte 10. Okay, byte 10. Now, if the window is now all acknowledged, right? If there's no more unacknowledged data in the window, we can stop the timer. There's no more outstanding data waiting for an ACK. And then another type of event that can happen in this state is if there's a timeout, the timer times out. And in that case, the sender will retransmit the segment that is associated with the smallest sequence number. So essentially, it's the oldest segment, right? The oldest unacknowledged segment. And then restart the timer, because we're not sure, right? We cannot be sure that this retransmission will go through, so we need to restart the timer. We may need to time out. We may time out again and may need to retransmit again. Any question here? Actually, let's go through a few scenarios. I think that will help the understanding. And then you can ask questions. All right, so this is first case of retransmission where the ACK is lost. So host A sends a segment. The sequence number of the segment is 92. And the segment contains 8 bytes of data. So that means in the payload, I have byte 92 all the way to byte 99, because I have 8 bytes, right? 92 to 99 is 8 bytes. That is the content of the segment. I assume that B receives the segment OK. So it needs to send back an ACK. And now the ACK number is going to be 100 because it has received up to byte 99 with no problem. So it just sends ACK 100 to tell host A that it expects to receive the next byte 100. But the ACK is lost, so there will be a timeout. The host A will simply retransmit upon timeout. And now we assume that the ACK is not lost. Okay, so this is one case of scenario. Now let's look at another case, which is a bit more interesting, which is a premature timeout. So even though TCP does all that kind of calculation to dynamically adjust the timer value, the premature timeout may still happen, right? Because there's this calculation for the timeout interval is not perfect. We cannot really predict the future. We can just make some kind of guesses, right? Best guesses. So here all of a sudden the network becomes more congested. So the ACK takes longer to get back to the sender, and the timer times out. All right, so here we host A send the first segment, sequence number 92. It contains 8 bytes of data. Okay, the next segment will start at byte 100, and that next segment contains 20 bytes of data. So the last byte here will be byte 119, right? Okay. Host B receive both segments OK. So here it will send ACK of 100. And here it's going to send ACK of 120. Okay, because this is a cumulative ACK, and it has received all the bytes up to and including byte 119. So it sends ACK of 120. When host A receives the ACK of 100, it will slide the window. So now send base is 100. Next, when it receives the ACK of 120, it will slide the window again to B to start at 120. However, in the meantime, the timer times out. Okay, the timer times out. So this packet will be retransmitted. And now note here, B at this point has received all the bytes up to 119 without gaps, right? No gaps. So it's going to send ACK of 120. ACK of 120. And when the host A receives ACK of 120, well, the window doesn't move because it's already at 120. Okay. Any question on these two scenarios? Okay, here we have another scenario, which is cumulative ACK. So this will show us why the cumulative ACK is a good idea. Okay. So I have like before, A will send 2 segments to B, right? 8 bytes, 20 bytes. B, he sends back ACK of 100, but this ACK is lost. But after that, when it receives the second segment, it's going to send ACK of 120. Okay, so even though ACK of 100 has been lost, host A, when it receives ACK of 120, knows that all the bytes have been received up to byte 119. So in other words, if A receives ACK of 120, this ACK of 100 is redundant. Actually, it's unnecessary, right? Because ACK of 120 carries more information than ACK of 100. And that is because this ACK is a cumulative ACK. So it doesn't matter even if there are some ACKs that are lost, right? In the past, as soon as the sender receives an ACK, then it gets the cumulative information about all the previous ACKs. Okay, so when it's ACK 120, then it can send, send the, this is the third segment, right? Which starts at byte 120. Okay, now I'm going to tell you about the logic at the receiver when to generate an ACK. So essentially, the idea here is, by the way, I just want to add one more thing. No, let's continue. I will get back to that later. All right, so the idea here is that very often when there's a TCP, the application sends a lot of data, meaning that you are going to have many segments. Many segments should be transmitted over the TCP connection. Okay, so typically it's not going to be one segment. Typically there will be many segments back to back. Okay, so the idea here is that we try to be more efficient so that we're not going to require the receiver to send an ACK at every segment that is received, but rather we try to consolidate the ACKs so that the receiver will send an ACK only for every 2 segments. Okay, every other segment that is received will result in an ACK sent by the receiver. And there's no problem to do that because the ACK is cumulative. So even if we skip sending an ACK, the next time we send an ACK, all the information will be there, right? There's no information lost. So that is the idea behind this table. All right, so let's look at the event at the receiver and then see what does the receiver do, okay, the action. So first, when the receiver receives a segment in order with the expected sequence number, right, everything is fine. And all the data up to expected sequence number is already ACKed. So to take an example, the receiver has sent back ACK of 10, right? ACK of 10. Now it receives a segment that has sequence number 10. Okay, meaning it starts with byte number 10. In that case, so it corresponds to this case, right? The receiver is going to delay the ACK. It's not going to send an ACK right away. It's going to wait a little bit, but it may wait up to, let's say, something like 500 milliseconds for the next segment. If the next segment does not arrive within this 500 milliseconds, it will send the ACK. Okay. Now, let's assume that we are in the case where the next segment arrives within 500 milliseconds. So it corresponds to this event. Arrival of another segment with expected sequence number. One other segment has ACK. So the other segment which has ACK pending is this one, right? The first one that for which we delay the ACK. So when the receiver receives the second segment, it's going to send right away a single cumulative ACK for both segments. Okay, now another type of event is the arrival of now out of order. So this is a gap, right? There's a gap out of order segment with a higher than expected sequence number. So receiver send back an ACK of 10. It expects to receive a segment with sequence number 10, but let's say it receives a segment with sequence number 100. So there's a gap out of order. So in that case, the receiver should send immediately a duplicate ACK. So it should send again ACK of 10. Send ACK of 10 right away. Okay, and we'll see later why we have this rule. Okay, no, do not wait. Send right away ACK of 10. Okay, now another type of event is the receiver receives a segment that partially or completely fills the gap. So again, take that example where the receiver receives up to byte 9, right, and send ACK of 10. And now it receives a segment that, well, it receives the segment for sequence number 100. So it sends ACK of 10, right? After that, so it receives a gap, right? There's a segment with a gap. Now, after that, it receives a segment that fills the gap, so partially fills the gap. So in this example, it will be a segment with a sequence number 10, because that's where the gap begins at byte. So it receives a segment with sequence number 10. It will send right away an ACK, provided that that segment starts at the lower end of the gap. Okay. So to take the same example, if it send back ACK of 10, and then it receives a segment with sequence number 100, there's a gap. But after that, if it's received a segment that fills the gap, but not starting at the lower end of the gap, meaning the sequence number of the segment is not, but it's something, it's, let's say 50, right? 50. So 50, the gap begins at 10 by 10. So if the segment is by a sequence number 50, it does not fill it does not start at the lower end of the gap. So the receiver will not send the ACK. But if the receiver receives a sequence number 10, after it has received a segment with sequence number 100, it will immediately send an ACK. And the ACK will be 10 plus, the sequence number of the ACK will be 10 plus the size of the segments that it has received. Okay, any question on this table? Okay, in the previous slide, the sender retransmitted segment 120. Why it did not retransmit 100 first? Okay, let's go back to the previous slide. This one. Okay, so the ACK is cumulative. Why do you say the ACK of both was lost? No, this ACK is not lost, right? This ACK is not lost. So when the A receives ACK of 120, the other one, you mean the other slide or what? Which slide? Are we looking at the same slide? Is this the right slide? Okay, let's go back one. Okay, where? Are you talking about the premature timeout? Okay. The sender retransmitted segment 120. Why did not retransmit segment 100? Okay, you're talking about this retransmission, yes. So here it retransmitted this segment because the timer was associated with this segment. So when the timer expires, it retransmits the segment that is associated with the timer. In this case, it is this segment that is retransmitted. Okay, all right. Yeah, there's no bad question, right? So it's important that I care very much about your understanding of the material. So do not hesitate to ask questions. If sometimes your question would take too long to answer, I may direct you to talk to me offline, or even better, post your question on Piazza. Okay, so this is the logic at the receiver, so that to be more efficient, right? So not necessarily the receiver does not have to send an ACK for every segment, and this worked pretty well because usually when you have TCP, you have the types of applications which are going to send many segments back to back. So just think streaming, right? Streaming. You're going to have TCP segments that are coming into the receiver, and this will work very well because, well, you know that if you receive a segment, you delay the ACK. There will be another segment that will come shortly after that, and then you can send the ACK. All right, let's look at the mechanism in TCP, which is called fast retransmit. So the TCP sender uses timeout, right, to retransmit, but the timer value can be relatively long, right? So which means there can be a long delay before you retransmit the lost packet. So ideally, we want to retransmit as soon as we are pretty confident that the packet has been lost, right? Okay, so now in order to do that, we are not going to just rely on the timeout, but we are going to also rely on the duplicate ACKs and use the duplicate ACKs as another way to detect packet loss. And this works pretty well also because, again, the application often, when it uses TCP, will send many segments back to back. And when you have a lost segment, there will likely be many duplicate ACKs. Okay, we'll see. I think it's on the next slide. We'll see more detail why, right? Why? But this is the logic for the TCP fast retransmit. So if the sender receives 3 ACKs for the same data, and that is referred to as triple duplicate ACKs or 3 duplicate ACKs, then it will resend the unacknowledged segment with the smallest sequence number. So to take an example, actually, let's defer that. It will be easier to look at the next slide. Here we have an example. We have many segments back to back, and these are my 2 segments. Let's assume that this one is lost. Okay, so host B here receives up to byte 99. So it sends ACK of 100. When it receives this segment, it will send again ACK of 100, right? Because there's a gap, and it has received only up to byte 99. When it receives the segment again ACK of 100, this one will again trigger ACK of 100. So here we see there are duplicate ACKs, right? ACK 100, which are duplicated. And we have 3 duplicate acts. So when I say 3 duplicate acts, I mean in total 4, right? 4 acts, the original act plus 3 duplicate acts. So in TCP, when the sender receives 3 duplicate acts, that will be construed as packet loss. And it will then retransmit the one that is the one that is indicated by the act, right? In this case, this one. So here you can see that this is a way to speed up the retransmission, because the timer, if you just use the timer, you perhaps may have to wait until this time to retransmit, right? But if you just use the 3 duplicate acts to detect packet loss, then you are able to transmit sooner, retransmit sooner. Okay, so let's go back to this slide. So if we see 3 duplicate, it will resend the unacknowledged segment with smaller sequence number. So in this case, the unacknowledged segment with the smaller sequence number is this one, because this one is unacknowledged, and it has the smallest sequence number among the ones which are unacknowledged. In this case, there's only one which is unacknowledged, which is this one, right? Okay, so now you may ask why 3 duplicate acts, right? Why 3? Why not 1? Because here in this example, this is already 1 duplicate act. So why not retransmit right away? Because this is a sign of packet loss. Why wait until you have 2 more duplicate acts? The reason here is that you may have duplicate acts when there's out of order delivery. So if you imagine that this packet, this segment, arrives after this one, okay? Because each of these segments is carried in one packet, and the packet may be delivered out of order. So it could very well happen that this segment arrives at the B before this one. So B will send back ACK of 100. And then that would be a case of duplicate ACK, but it does not necessarily mean that it is packet loss, right? It could be out of order delivery. And that is the reason why they set it to 3. So there's nothing scientific about the value 3. But if there are 3 duplicate acts, there's a high confidence or high likelihood that it is packet loss and not out of order delivery. Okay, so if you just set to 1, then there's still a chance that it is out of order delivery. You don't want to retransmit yet. Okay. Any question on TCP fast retransmit? So essentially, TCP uses two mechanisms, right, to retransmit to detect packet loss. One is timeout. The other one is 3 duplicate acts. And this tends to work pretty well because, as I said earlier, very often the application will send many segments back to back. So that will trigger the duplicate acts. Okay, if there's no question, then let's do a checkpoint. And today we'll also do 2 checkpoints. All right, what is the, let me see the, okay, 7-1. By the way, we are a little bit behind. So what I mean is checkpoints are a little bit behind the lectures. So if your memory is not fresh because the lecture is older, right? Then you can very well wait, right, and read again the units before you take the checkpoint. And you can recognize which unit because the checkpoint number starts with the unit number. Okay, so for example, checkpoint 7-1 means that it will test you on Unit 7. So you may want to read again Unit 7 before you take the checkpoint. Okay, so let's start with 7-1. Okay, this is the password for checkpoint 7-1. Okay, so let's go back to the lectures. All right, so we have been looking at how the data is transferred, how TCP does reliable data transfer, right? How does it detect packet loss to retransmit? But before we can do all of that, we need to set up a TCP connection. So let's see how that is done. So setting up the TCP connection means in particular that the two endpoints must agree on the parameters to be used for the connection. And by the way, here the slide says sender and receiver, but keep in mind that a TCP connection is bidirectional, okay? So when we say sender and receiver, we are focusing on one direction of TCP. But when you set up a TCP connection, you need to do that setup for both directions. Okay, so for one direction, let's say from A to B, A will be the sender, B will be the receiver. But then at the same time, you need to set up for the other direction where B will be the sender and A is the receiver. And here are the main parameters. So one is, okay, question about the code. Okay, so let me put it in the chat for you. Or does anyone have it? Perhaps you can type faster than me. So, okay, thank you, James. Yeah, I can see that you do type faster than me. So, okay. All right, so some of the most important connection parameters. Remember the sequence number? I told you that it does not necessarily start at 0 or start at 1. It is some number that is chosen by the sender. So now, because TCP connection is bidirectional, A will be the sender in one direction, B will be the sender in the other direction. So A will choose the initial sequence number for the data that it will send to B, and B will choose the initial sequence number for the data that it will send to A. Okay, so that's what we have here. Sequence number, client to server, server to client. So here we assume that we have a TCP connection between the client and a server. But from the viewpoint of TCP, it is bidirectional, right? Okay, so we need to agree on the initial sequence number for the data sent from the client to the server, and for the data sent from the server to the client. So these are the two parameters here. Also need to agree on the receiver buffer size. So the receiver, each of these guys is a receiver. So each of these guys will have a receiver buffer with a size. and they need to be told to the other end so that the other end will not overwhelm the receiver buffer size. Okay. And then there are a few more things, such as TCP options and so on, but I'm not going to go into these details. But essentially what you see is that you need to set up a TCP connection before you can send data over the TCP connection. Also, another reason you need to set up the TCP connection is that the server needs to create a new socket, remember? Need to create a new socket that will be dedicated to a particular client because the TCP sockets are mapped one-to-one. So here we have the corresponding part in the code. At the server side, you're going to you have created a welcoming socket, and then you wait on the welcoming socket for any request coming from a client, and accept that request, right? And when the request is accepted, it will create a new socket, which is called connection socket. Okay, at the client side, actually the whole thing is initiated by the client. And at the client side, the client will create a socket called client socket. And the socket will specify when it creates a socket, what is the host name and what is the port number on the server side. All right, so let's look at the dynamics of the TCP connection setup. It's going to use a three-way handshake. It is always initiated by the client. So the client will choose the initial sequence number for the data that will be sent in this direction. Let's call that sequence number X, whatever it is, right? So it's going to send a special message. It's called a SYN message, TCP SYN message to the server. That TCP, so let me go back to okay, remember this slide? So the SYN message is nothing but a segment, a TCP segment. So it will have this header, but to indicate that it is a SYN message, the SYN bit will be set. Okay, so there's a 1-bit flag that is called the SYN bit here, and when it is set, that means that it is a SYN message. And that is what is sent by the client to the server. And then later we will see there are other TCP control messages. In particular, there's the FIN, which is a message simply when you set this bit F to 1. Right? When it is set, then it is a FIN message. Okay, so this is that message, TCP SYN message. And remember, because in the TCP header, there's a sequence number, right? So that sequence number is X, it will be X. So that X that is chosen by the clients will be X. Now, when the server receives that message, it needs to do two things. So essentially, this message will initiates the setting up of one direction of the TCP connection, which is the direction from the client to the server. So when the server receives this message, it needs to do two things. It needs to acknowledge this message, and then it also needs to initiate the other half of the connection, which is the direction from the server to the client. Okay. So in reality, when you set up a TCP connection, you are going to set up two halves of the connection. Okay, each half is one direction. So the server will now choose an initial sequence number, let's call it Y, that will be used for the data sent in this direction. And then it will send this message, which is called a SYN-ACK. This is the name of the message, SYN-ACK. And again, it is it has a TCP header where the SYN bit is set to 1 because SYN. So actually, SYN-ACK means two things combined into one message. It is a SYN message for the other direction. It is also an ACK of this SYN. Okay, so it has to acknowledge this SYN, but at the same time, it needs to send a SYN for the other direction from server to client. And that is why the message is called a SYN-ACK. And in the TCP header, the SYN bit will be set to 1 to indicate a SYN. The ACK bit is set to 1 to indicate that it is ACKing, and then it will use the same acknowledgement mechanism that we have learned about, where the ACK number will be this sequence number plus 1. Okay, and it sends sequence number Y, which is the initial sequence number that it has chosen. Okay, now the client when the client receives a SYN-ACK message, it knows that the connection, the first half of the connection, which is for the data transfer from client to server, has been set up, right? Because the server has acknowledged this message. So that indicates that the server is live, and from this point on, actually, this half of the connection is open. Okay, but it also needs to acknowledge this message, which is what it does here. So it sends back a ACK, and the acknowledgement number is Y plus 1. So it follows the same scheme for acknowledgement of data, right? Send ACK plus 1, and that will tell the server that the setup of the second half of the connection is done, that this message has been received by the client, and the second half is done. So we have set up both halves of the TCP connection, so the whole TCP connection is set up. Okay. So here the client knows that the server is alive, and when the server receives this ACK, it knows that the client is live, and we are done. Essentially, we have set up the TCP connection, and it is a three-way handshake because it involves 3 messages. And actually, this message is logically 2 messages into 1, right? Because it acknowledged this message, but it is also a SYN for the other direction. Any question here? Okay, now if we look at the FSM for the three-way handshake, so initially on both the client server side, the state is closed. Okay, so it all starts with at the server creating the welcoming socket, and also at the server it receives a request from a client through the welcoming socket, which is what we see here. Receive a request, so it's going to go to the listen state, and here assume that it received the SYN from a client, some client, right? Because this is the trigger. So this is the client side. What we have on the right is what happens on the client side. What we have on the left is what happens on the server side. So on the client side, when we have that socket creation, that will automatically trigger the sending of the SYN message to the server. and the client will go into this state, SYN sent. Okay. Now on the server side, in the listen state, when it receives a SYN message from a client, then it will create that new socket. Remember that new socket for communication with the client. But the welcoming socket is already there, right? So create a new socket, and then this will go into the state called SYN receive, where it's going to wait for the ACK from the client. So it will receive the ACK from the client. It will go to the established state. Now on the client side, after the client has sent the SYN, it will go into this state where it waits for the SYN ACK from the server. So when it receives the SYN ACK from the server, it will also go to the established state. And the established state is the state where the TCP connection has been set up. Okay, actually, let's take a break now. Okay, let's take a 5-minute break and be back at 1:42.